The lamp on your bedside table is doing something impossible. Not metaphorically impossible. Not impossible in the casual way people use the word to mean surprising or unlikely. Physically impossible, in violation of every rule about how matter and energy were understood to behave for the 200 years before a small group of physicists working in the early decades of the 20th century discovered that the rules were wrong. The filament inside the bulb, or the semiconductor, if it is an LED, is releasing light because electrons inside it are losing energy. An electron drops from a higher energy state to a lower one, and the difference in energy leaves the material as a photon, a particle of light that travels across the room and arrives at your eye. This process happens billions of times per second in a lamp that is on, and every single instance of it is at the level where the physics actually operates, an event with no precise location, no precise timing, and no definite outcome until the moment it occurs. The light reaching your eye right now was produced by a process that quantum mechanics describes with extraordinary precision, and that nobody, not the physicists who developed the theory, not the engineers who built the lamp, not anyone working in physics today, can fully explain in terms of what is actually happening. Tonight, we begin at the beginning of the strangest and most precise and most deeply unresolved story in the history of science. And we begin slowly because it deserves nothing less. If these quiet journeys help you rest, consider leaving a like or subscribing. But for now, let the lamp do its impossible work, and let your eyes close, and let the story begin. You are lying in a room. The room is built from matter. Walls, floor, ceiling, the furniture arranged within it, the blankets around you. All of it is matter. All of it is, at the level of its fundamental composition, almost entirely empty space. The atom, the basic unit of which all ordinary matter is composed, consists of a nucleus at its center containing protons and neutrons packed together in a space almost inconceivably small, surrounded by electrons that occupy a region of space roughly 100,000 times larger than the nucleus itself. If the nucleus of a hydrogen atom were the size of a marble, a small glass sphere you could hold between two fingers, the electron would be orbiting at a distance of roughly 1 kilometer. Everything between the marble and the kilometer-distant electron is empty. Your hand, pressed against the wall beside you, does not touch the wall in any meaningful physical sense. The electrons in the outermost atoms of your skin come close to the electrons in the outermost atoms of the wall, and the electromagnetic repulsion between them prevents further approach. And this is what the sensation of solidity is. A force, not a contact, operating across the empty space between particles that never actually meet. This is the world that classical physics, the physics of Newton, of Maxwell, of the entire 19th century, described accurately and well at the scales where it operates. And then physicists began looking closer. The crisis that would eventually produce quantum mechanics did not begin with a single dramatic discovery. It began with two problems. Two places where the predictions of classical physics met the results of careful experiment and disagreed, not slightly, not in ways that might be explained by experimental error or instrument imprecision, but fundamentally, irreconcilably, in ways that could not be adjusted away. The first problem was light. Classical physics, specifically Maxwell's equations describing electromagnetic waves, predicted that light waves should propagate through a medium the way sound waves propagate through air and water waves propagate through water. This medium was called the luminiferous ether. It was assumed to fill all of space. It had never been detected, but its existence seemed logically necessary because waves require a medium through which to travel. In 1887, two American physicists named Albert Michelson and Edward Morley designed an experiment to detect the ether, specifically to measure the difference in the speed of light in different directions, which should exist if the Earth is moving through the ether as it orbits the Sun, the way a boat moving through water experiences different resistances from different directions. They measured. There was no difference. The speed of light was the same in every direction, regardless of the Earth's motion, to within the precision of their extraordinarily sensitive instrument. The ether did not exist. And if the ether did not exist, then light was a wave that propagated without a medium, something that classical physics had no framework for understanding. The second problem was heat. When you heat an object, a piece of iron, a ceramic plate, the filament of a lamp, it emits radiation. At low temperatures, it glows red. At higher temperatures, orange, then yellow, then approaching white. The color shifts because the distribution of energy across the different frequencies of emitted radiations changes with temperature. Classical physics predicted how this distribution should look. The prediction worked reasonably well at low frequencies. At high frequencies, at the blue end of the spectrum and beyond, the classical prediction diverged catastrophically from what was actually observed. Not slightly wrong, infinitely wrong. The classical equations predicted that the amount of energy emitted at very short wavelengths should increase without limit, that a heated object should emit infinite energy in the ultraviolet and beyond. This was so obviously incorrect, so dramatically at odds with the simple fact that heated objects do not explode with infinite radiation, that it was given a name: the ultraviolet catastrophe. Something in the classical description of how matter and radiation interacted was fundamentally broken. In Berlin, in the late 1890s, a physicist named Max Planck was working on the black-body radiation problem, the technical name for the question of how heated objects emit light. With the patient, methodical approach of someone who has spent decades doing careful physics and understands that good work requires time, Planck was not, by temperament, a revolutionary. He was a conservative physicist who believed in the classical framework and wanted to fix the radiation problem within it, not abandon the framework that had produced so much successful physics over the previous 2 centuries. His study was a quiet room in a city that was, in the late 19th century, one of the centers of the scientific world. Books on the shelves, papers on the desk, the kind of organized working environment that careful, serious thought produces over years of occupation. He worked on the problem for years. He tried different mathematical approaches. He modified the equations. He looked for a way to make the classical prediction match the observed distribution of radiation across all frequencies, not just the low ones. He could not find one. What he found instead, in the autumn of 1900, working backward from the experimental data to the equation that would produce it, was a mathematical formula that fit the observations perfectly across all frequencies. It was not derived from first principles. It was not built up from known physics. It was extracted from the data, constructed to fit, and then examined to understand what it implied. What it implied disturbed him. The formula worked only if energy was not continuous. In classical physics, energy could take any value. You could have any amount of it in any proportion, distributed in any way. It was a smooth, continuous quantity, like the water in a river, divisible into arbitrarily small portions. Planck's formula required that energy came in discrete chunks, that when a heated object emitted radiation, it did not release energy in a smooth, continuous flow, but in specific, indivisible units. Packets of energy whose size was determined by the frequency of the radiation and a constant that Planck introduced into the formula. He called this constant H. He did not believe that these energy packets were real. He believed they were a mathematical fiction, a calculational trick that produced the right answer without necessarily corresponding to anything physically genuine. He expected that someone would eventually find a way to derive the same result without assuming discrete energy units, and that the discreteness would turn out to be an artifact of the mathematics rather than a feature of reality. That someone did not arrive because the discreteness was not an artifact. It was the most important discovery in physics since Newton. Outside Planck's study, Berlin was a city in the last years of a century that had believed with increasing confidence that the major questions of physics were close to being answered. The frameworks existed. The equations were written. The precision of the instruments was improving year by year, confirming prediction after prediction. Two problems remained, two places where the predictions failed. Planck had found a formula that fixed one of them. He had fixed it by introducing something he did not believe was real. 5 years later, a 26-year-old patent clerk in Bern would take Planck's mathematical fiction and propose that it was, in fact, describing reality. That proposal would begin the reconstruction of physics from its foundations. A reconstruction that has been underway for 100 years and is not yet complete. The lamp on your bedside table is the product of that reconstruction. The electrons inside it are jumping between energy levels that Planck's constant governs, releasing photons whose energy is determined by the frequency of the light they carry, traveling across the room at a speed that has no medium to travel through, arriving at your eye through a process that the most precise mathematical theory in the history of science describes with extraordinary accuracy, and that nobody has ever fully explained. The room around you is quiet. The lamp does its impossible work, and the story of how we found all of this out, slowly, carefully, by following the mathematics wherever it led, even when it led somewhere that made no intuitive sense, begins here. In a Berlin study with a man who introduced a number he did not believe was real. Physics in the closing years of the 19th century had the particular confidence of a discipline approaching completion. Not arrogance, exactly. The physicists of the 1890s were careful people, trained in precision and skeptical of overstatement. But there was, in the literature, and the lectures, and the correspondence of the era, a settled quality, a sense that the major structures had been erected, and what remained was refinement rather than reconstruction. Newton's mechanics governed the motion of everything from falling apples to orbiting planets, confirmed by 2 centuries of observation to a precision that left no meaningful room for doubt. Maxwell's equations described the behavior of electric and magnetic fields, predicted the existence of electromagnetic waves, and had been confirmed experimentally by Heinrich Hertz in 1887. The same year the first crack appeared. Thermodynamics described heat and energy and the irreversible tendency of systems toward disorder. Statistical mechanics, developed by Boltzmann and Maxwell, connected the microscopic behavior of atoms to the macroscopic properties of gases and solids. The frameworks existed, the equations were written, the instruments were improving year by year. Lord Kelvin, one of the most eminent physicists of the era, reportedly remarked that there were only 2 small clouds on the horizon of physics. Those clouds were the Michelson-Morley result and the ultraviolet catastrophe. They were not small, and they were not on the horizon. Albert Michelson had been trying to measure the speed of light more precisely than anyone had managed before. He was an American physicist with a particular gift for experimental design. The kind of scientist whose contribution lies not in theoretical insight, but in the construction of instruments capable of measurement previously considered impossible. He had already made the most precise measurement of the speed of light obtained to that point when, in the mid-1880s, he turned his attention to the question of the ether. The luminiferous ether was not a fringe idea. It was the consensus of physics. Maxwell's equations described light as a transverse electromagnetic wave, and waves, in the understanding of 19th century physics, required a medium through which to travel. Sound was a wave in air. Water waves were waves in water. Light waves were waves in the ether. A medium that permeated all of space, that was stationary with respect to the universe as a whole, and through which the Earth moved as it orbited the Sun. If the Earth was moving through the ether, then the speed of light should appear slightly different in different directions, faster when measured in the direction the Earth was moving, slower when measured against it. The way a boat moving through water experiences the current differently from different directions, the difference would be tiny. But Michelson had designed an instrument sensitive enough to detect it. He conducted the experiment in 1881, alone in Berlin. He found no difference. He was not entirely satisfied with the result. The instrument had vibrated. The basement where it was housed had not been stable enough. He returned to the problem in 1887, this time in collaboration with Edward Morley at what is now Case Western Reserve University in Cleveland. They mounted their apparatus on a massive stone slab floating in a pool of liquid mercury, eliminating the vibration. They ran the experiment repeatedly in different orientations through different seasons, so that if the Earth's motion relative to the ether changed throughout the year, the change would be visible in the data. The apparatus was sensitive enough to detect the expected difference. The expected difference was not there. Michelson and Morley published their result in the American Journal of Science in 1887. The paper was careful and precise, and its conclusion was stated without drama in the measured language of experimental physicists reporting what they had found. Now, they had found nothing, no difference in the speed of light in any direction, no evidence of motion through the ether, no ether. The response from the physics community was, initially, a mixture of discomfort and creative denial. Various explanations were proposed: that the ether was dragged along by the Earth, that objects contracted slightly in the direction of motion through the ether in a way that exactly canceled the expected effect. The Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz both proposed versions of this contraction hypothesis independently, and the mathematics worked out correctly. But the explanation was ad hoc. It was constructed specifically to explain the null result, without independent motivation, without predicting anything new. It preserved the ether by making it permanently undetectable. A permanently undetectable ether was, in the view of at least some physicists, an ether that did not need to exist. The first cloud sat on the horizon, growing slowly larger. The second problem was less dramatic in its origin, but more mathematically precise in its failure. A black body is a theoretical object, an idealized surface that absorbs all radiation that falls on it, and emits radiation in a way that depends only on its temperature. Real objects approximate this behavior to varying degrees. A piece of iron heated in a furnace comes reasonably close. The question of how a black body distributes the energy it emits across different frequencies of radiation, the shape of what physicists call the black body spectrum, had been studied experimentally throughout the 1880s and 1890s, with 1880s with increasing precision. The data were clear and reproducible. The spectrum had a characteristic shape. It rose from zero at low frequencies, peaked at a frequency that increased with temperature, and fell back toward zero at high frequencies. The challenge was to derive this shape from first principles, to calculate it from the known laws of physics and show that those laws predicted what was observed. Several physicists attempted this. The results were consistently partial. Wilhelm Wien derived a formula in 1896 that matched the experimental data well at high frequencies, but diverged from it at low frequencies. Lord Rayleigh, working from classical statistical mechanics, derived a formula that matched the data well at low frequencies, but predicted that the energy emitted should increase without limit as the frequency increased. The ultraviolet catastrophe, a result so clearly wrong that it required no experimental test to refute. The two formulas worked in different regions and failed in each other's region. No single formula derived from classical physics matched the data across all frequency. Max Planck had been following this problem for years. He was 42 years old in 1900, a professor at the University of Berlin, respected and established, the kind of scientist who contributes steadily and carefully over decades rather than producing occasional dramatic breakthroughs. He had spent much of his career working on thermodynamics and entropy, and he brought this background to the blackbody problem with the patience of someone who understood that difficult problems sometimes required sustained attention rather than sudden inspiration. Through the summer and autumn of 1900, he worked on the problem intensively. He was in correspondence with the experimenters who were measuring the blackbody spectrum with increasing precision, and he received updated data that showed clearly what the complete shape of the spectrum looked like across all frequency. He proceeded, he later wrote, as an act of desperation. He found a mathematical interpolation, a formula that connected Wien's high-frequency expression with Spratio, with Rayleigh's low-frequency expression in a way that matched the experimental data across the entire spectrum. He presented this interpolation formula to the German Physical Society on October 19, 1900. It fit the data perfectly, within experimental precision across all frequency. Now he had to understand why. He spent the following weeks working backward from the formula, trying to derive it from physical assumptions, to find the model of how matter and radiation interacted that would produce, as a natural consequence, the equation he had found empirically. The derivation he arrived at required him to assume that the energy exchanged between the irradiating material and the electromagnetic field could not take arbitrary values. It had to come in discrete multiples of a basic unit, a quantum of energy whose size was proportional to the frequency of the radiation, and a constant that appeared in the formula. He called the constant H. Its value, determined by fitting the formula to the experimental data, was approximately 626 times 10 to the negative 34th joule seconds, an extraordinarily small number, which was why the discreteness of energy was not apparent in everyday experience. At human scales, the energy packets were so tiny that energy appeared continuous, the way a beach appears sandy rather than granular from a distance. Planck presented the full derivation on December 14, 1900. He described it himself, years later, as the most reluctant revolutionary act in the history of physics. He had introduced the quantum of energy not because he believed energy was actually discrete, but because it was the only assumption that produced the correct formula. He expected and hoped that someone would find a way to derive the same result without the discreteness assumption. No one did. The year 1900 ended with two clouds that had become impossible to ignore. The Michelson-Morley result had eliminated the ether and left light as a wave without a medium, a fact that classical physics had no framework for accommodating. Planck's formula had described blackbody radiation with perfect precision at the cost of assuming that energy was not continuous, an assumption that contradicted everything classical physics had established about the nature of physical quantities. Both problems would be resolved, but their resolution would require abandoning not just specific theories, but the entire conceptual framework that classical physics had built over 2 centuries. The physicist who would take the first step toward that abandonment was not yet working on either problem in 1900. He was 21 years old, recently graduated, unable to find an academic position, about to begin work at a patent office in Bern. His name was Albert Einstein, and in 5 years working alone, in the hours before and after examining other people's inventions, he would publish 4 papers that would change physics permanently. One of them would take Planck's energy quantum seriously, more seriously than Planck himself had intended, and propose that light was not a wave at all. The room where Planck had done his December derivation was quiet now, late in the year, the winter cold settling into the stone of the university buildings. The formula sat on the page, correct and disturbing, and somewhere in the mathematics of it, the quantum age was waiting to begin. The patent office in Bern occupied a building on the Speichergasse, a few minutes' walk from the clock tower that had stood at the end of the Kramgasse since the 12th century. Albert Einstein arrived there in June 1902, 23 years old, hired as a technical expert, 3rd class at an annual salary that was modest but sufficient. His job was to read patent applications and determine whether the inventions they described were original. whether they worked as claimed, and whether the descriptions were precise enough to be legally protected. He was good at it. The work suited a mind that could identify the flaw in a technical argument quickly and precisely, that could see the gap between what a device was claimed to do and what it actually did. He finished his assigned work efficiently, often before the end of the official working day, and spent the remaining time thinking about physics, not the physics of the patent applications, his own physics. The problems that had been forming in his mind since he was 16 years old, and had first asked himself what it would look like to ride alongside a beam of light. One of those problems was Planck's quantum. Planck had introduced the energy quantum as a mathematical necessity, a constraint he imposed on the calculation, because it was the only assumption that produced the correct formula. He did not believe the quantum was physically real. He believed it was a calculational artifact, a feature of the mathematics that would eventually be explained away by a deeper derivation, Bloch-Brandeis, rooted in classical physics. Einstein read Planck's 1900 paper in the way that certain minds read important work, not to understand what the author was claiming, but to understand what the mathematics was actually saying, whether or not the author had followed it all the way to its conclusion. Was saying, what Einstein concluded was that energy quanta were real, not a fiction, not a mathematical trick, actual, discrete packets of energy that light carried and delivered and consisted of. This was a larger claim than Planck had made, and a more radical one. Planck had proposed that matter could only absorb and emit energy in discrete units. Einstein proposed that light itself was made of discrete units, that the continuous electromagnetic wave of Maxwell's equations was not the complete picture of what light was. He called these units light quanta. The word photon would come later, coined by the chemist Gilbert Lewis in 1926. The evidence Einstein used to support this proposal was not the blackbody spectrum. It was a different phenomenon entirely, one that had been puzzling experimenters for 2 decades and that nobody had connected to Planck's work. The photoelectric effect was the observation that when light shines on certain metal surfaces, electrons are ejected from the surface. This, in itself, was not surprising. Light carries energy. Energy absorbed by electrons in the metal might be sufficient to free them from the surface. What was surprising was the way the ejection depended on the properties of the light. Classical physics predicted that the energy of the ejected electrons should depend on the intensity of the light. Brighter light carrying more energy, producing faster electrons. The frequency of the light, its color, in the visible range, should not matter except insofar as different frequencies might be absorbed more or less efficiently by the metal. The experimental results showed exactly the opposite. The energy of the ejected electrons depended entirely on the frequency of the light, not the intensity. Below a certain threshold frequency, no electrons were ejected at all, regardless of how bright the light was. Above the threshold, electrons were ejected immediately, even in very dim light, with an energy that increased linearly with frequency. Intensity affected only the number of electrons ejected, not their energy. Classical physics had no explanation for this. Einstein's explanation was immediate and precise. If light consists of discrete packets, photons, each carrying an energy proportional to its frequency, then the photoelectric effect makes perfect sense. A single photon interacts with a single electron. If the photon's energy, determined by its frequency, is above the threshold required to free the electron from the metal surface, the electron is ejected, carrying the excess energy as kinetic motion. If the photon's energy is below the threshold, no ejection occurs, regardless of how many photons arrive, because each photon interacts with only one electron, and no individual photon has enough energy to do the job. Higher frequency means higher energy per photon, which means faster ejected electrons. More intense light means more photons, which means more ejected electrons, but no change in their individual energies. The mathematics matched the experimental data precisely. Einstein published this paper in 1905 as one of 4 papers he produced that year while working at the patent office. The papers covered the photoelectric effect, Brownian motion, special relativity, and the equivalence of mass and energy. He was 26 years old. He submitted all 4 papers to the Annalen der Physik within a few months of each other between March and September 1905. Each one was important. The photoelectric paper was the one for which he would eventually receive the Nobel Prize in 1921, not for relativity, which remained controversial among the Nobel Committee for years, but for the photoelectric effect, which was experimentally confirmed and theoretically precise. The confirmation came from Robert Millikan. Millikan was an American experimental physicist who spent 10 years between 1905 and 1915 designing and executing experiments specifically intended to test Einstein's photoelectric equation. He did not believe the equation was correct. He found the idea of light quanta conceptually objectionable. It contradicted the wave theory of light, which had been established by 2 centuries of experimental evidence, and was supported by Maxwell's equations, which had themselves been confirmed to high precision. Millikan expected his experiments to disprove Einstein's proposal. His experiments confirmed it. Every prediction of Einstein's equation matched the data. The relationship between frequency and ejected electron energy was exactly linear, with exactly the slope that Einstein had predicted. The threshold frequency below which no electrons were ejected corresponded exactly to the binding energy of electrons in the metals Millikan tested. Most importantly, Millikan's experiments provided an independent measurement of Planck's constant, H, the same number that Planck had introduced in his 1900 blackbody formula and found from completely different experimental data. Exactly the same value, the same constant appeared in two completely different phenomena, measured by completely different methods. It was not a coincidence. It was a signature. The quantum was real. Millikan published his results in 1916. He was not pleased. He had spent 10 years attempting to disprove Einstein's light quantum hypothesis and had instead produced the most precise confirmation of it available. He received the Nobel Prize in Physics in 1923, partly for this work. The physics community's response to the light quantum was not immediate acceptance. Even after Millikan's confirmation, many physicists resisted the idea. The wave theory of light had too much evidence behind it. Diffraction, interference, the entire body of 19th century optics to be simply discarded. Light demonstrably behaved as a wave in experiments designed to reveal wave behavior, and now it was being claimed to behave as a particle in experiments designed to reveal particle behavior. Both things appeared to be true. This was not supposed to be possible. A particle has a definite location at any given moment. A wave is spread out through space, existing simultaneously across an extended region. Something cannot be both, or so every intuition built from everyday experience insisted, and yet the mathematics said it was both. And the experiments confirmed the mathematics. The discomfort this produced among physicists was genuine and significant. These were not people who resisted new ideas on principle. They had built their careers on following evidence wherever it led. But the evidence was leading somewhere that seemed to require abandoning the principle of logical consistency that physics had always taken as fundamental. A thing was one thing or another. It was not both. The quantum said otherwise. In the patent office on the Speichergas, Einstein continued his work through 1905 and into the following years. He examined applications. He wrote his assessments. He walked to and from the office through the old city of Bern. The clock tower chimed the hours he passed beneath it. The 4 papers he had published in his extraordinary year circulated through the physics community, read carefully by the people who understood their implications, and more cautiously by the people who did not yet know what to make of them. Planck read the photoelectric paper and was troubled by it. He had introduced the quantum as a mathematical convenience and found that Einstein had taken it seriously and used it to a physical reality and used it to explain something Planck himself had not attempted to explain. He thought Einstein had gone too far. He was wrong. The quantum was real. The light was made of it. The electrons could only be freed by it in precise, individual interactions that no wave theory could account for. And the deeper implications of all of this, what it meant for the nature of matter, for the structure of the atom, for the structure, for the very concept of physical reality, were only beginning to become visible. The lamp in the room was burning. The photons were traveling. The electrons were waiting to be asked what they were. Nobody had yet found the courage to ask directly. That would take another decade, and a young Danish physicist who was willing to follow the mathematics into territory that classical physics had declared impossible. Ernest Rutherford was not a subtle man. He was a large, loud, energetic New Zealander who had arrived in England in 1895 on a scholarship and proceeded to do more experimental physics in the following decades than most laboratories managed in a generation. His students described him as a force of nature, physically present in a way that made rooms feel smaller, intellectually direct in a way that made complicated problems feel solvable. In 1909, working at the University of Manchester with his collaborators Hans Geiger and Ernest Marsden, he directed a beam of alpha particles, positively charged particles emitted by radioactive materials, at a thin sheet of gold foil. The expectation, based on the prevailing model of the atom, was that the alpha particles would pass through the foil with minor deflections. The atom, in the model proposed by J.J. Thomson in 1904, was a diffuse sphere of positive charge with electrons embedded within it, like raisins in a pudding, spread out, soft, offering no concentrated resistance to a passing particle. Most of the alpha particles passed straight through, but some deflected at large angles, and a small number. Rutherford described his astonishment in a letter as equivalent to firing artillery shells at tissue paper and having them bounce back, reflected almost directly backward. The atom was not a diffuse sphere. It had a core, a small, dense, positively charged nucleus at its center, containing almost all of the atom's mass, surrounded by a vast empty space in which the electrons moved. Rutherford published his nuclear model of the atom in 1911, and the problem was immediately apparent to anyone who thought carefully about the physics. An electron orbiting a nucleus is, in classical physics, an accelerating charge. Acceleration of a charged particle produces electromagnetic radiation. This was one of the firmly established results of Maxwell's equations, confirmed experimentally, not a matter of theoretical dispute. An electron in a circular orbit is continuously accelerating toward the center. Changing direction constitutes acceleration, even at constant speed. Therefore, it should continuously emit radiation. Emitting radiation means losing energy. Losing energy means the orbit shrinks. The electron spirals inward as it loses the energy that was keeping it at its orbital distance. The calculation was straightforward. An electron in the innermost orbit of a hydrogen atom should spiral into the nucleus in approximately 100 picoseconds, 1/10 billionth of a second. Every atom in the universe should have collapsed within a fraction of a second of its formation. The chair beneath you should not exist. The air around you should not exist. You should not exist, and yet everything existed and had existed for billions of years. In complete defiance of what classical physics said was possible, Niels Bohr arrived in Manchester in 1912 to work with Rutherford as a postdoctoral researcher. He was 26 years old, Danish, recently completed his doctoral thesis on the electron theory of metals. He was quiet where Rutherford was loud, careful where Rutherford was direct, inclined to sit with a problem for a long time before speaking about it. He sat with the atomic stability problem through his months in Manchester and through the following year in Copenhagen, where he had returned to a lectureship at the university. The solution he arrived at was not derived from classical physics. It was imposed on the physics from outside, a set of rules that had no classical justification, but that produced the right answer in the same way that Planck's discreteness assumption had produced the right black-body formula without classical justification. Bohr proposed that electrons in atoms could only occupy specific orbits at specific distances from the nucleus, corresponding to specific energies. Not any orbit, the way a satellite can orbit the Earth at any altitude. Only certain orbits separated by gaps. An electron in one of these allowed orbits did not radiate. It simply moved indefinitely without losing energy, in violation of Maxwell's equations. The classical prohibition on stable orbits simply did not apply. When an electron moved from a higher orbit to a lower one, when it jumped, it emitted a photon carrying the energy difference between the two orbits. This energy was specific and precise, determined by the difference between the two orbital energies, and it corresponded to a specific frequency of light. When an electron absorbed a photon of exactly the right energy, it jumped upward to a higher orbit between the allowed orbits. The electron did not travel. It did not gradually move from one to the other. It disappeared from one and appeared in the other, instantaneously, without traversing the space between. The prediction this model made was specific and testable. If electrons could only occupy specific energy levels, then hydrogen atoms could only emit and absorb light at specific frequencies, the frequencies corresponding to the energy differences between allowed orbits. Hydrogen should have a discrete spectrum, bright lines at specific wavelengths, dark gaps. Everywhere else, hydrogen did have a discrete spectrum. It had been observed and catalogued since the 1880s, when a Swiss mathematics teacher named Johann Balmer had found a simple formula describing the wavelengths of 4 visible hydrogen spectral lines without understanding why the formula worked. Bohr's model explained why the formula worked. His calculation of the hydrogen spectrum matched the observed spectral lines precisely, not approximately, precisely to the accuracy of the available measurements. He published his model in 1913 in a paper that is still studied in physics courses today. The response was complicated. The model worked, and working was hard to argue with. Einstein, shown Bohr's paper, called it one of the greatest discoveries in physics. But the model made no physical sense in classical terms. Electrons that don't radiate in orbit, instantaneous jumps between energy levels with nothing in between. Specific orbits selected by rules that had no derivation, no justification, no connection to any existing physical principle. Bohr himself was aware of this. He did not claim to understand why electrons behaved this way. He claimed only that they did and that the mathematics described the behavior correctly. This was a new kind of physics, one in which the rule was to follow the mathematics even when the mathematics led somewhere physically inexplicable. It was uncomfortable, it was productive, and it was only the beginning of the strangeness. The Copenhagen of 1913 was a city in the particular quality of a northern autumn. The light low and amber in the afternoons, the harbor cold, the streets quiet in the evenings. Bohr worked in his university office through those months, checking his calculations, writing the paper, corresponding with Rutherford about the results. The nucleus sat at the center of the atom, dense and small and positively charged. Exactly as Rutherford had found, the electrons sat in their allowed orbits around it, stable and silent, not radiating, not spiraling inward, simply present at their permitted distances. In defiance of Maxwell, in defiance of 2 centuries of classical physics, in complete agreement with the spectral lines of hydrogen observed in laboratory grotto across Europe, the atom held together. It always had. Now, for the first time, there was a reason, not a classical reason, not an intuitive reason, but a mathematical reason that worked to understand why. Outside the window, the harbor was dark. The city settled into its evening quiet, and in the allowed orbits of every hydrogen atom, in every molecule of water, in that harbor, the electrons held their positions, patient and stable, waiting for the next chapter of their explanations. Louis de Broglie was a French aristocrat who had studied history before turning to physics. He was the younger son of the 5th Duc de Broglie, born into a family whose military and diplomatic history stretched back through several centuries of French public life. His older brother, Maurice, had become a physicist and maintained a private laboratory in Paris where he conducted research on X-rays. Louis had followed Maurice into physics. After a period studying medieval history at the Sorbonne, drawn by something he found in the theoretical questions of the new quantum physics that history could not provide, he was working on his doctoral thesis at the University of Paris in 1923, when he had the idea that his thesis committee would not know how to evaluate. The idea was simple to state and radical in its implications. Einstein had shown that light, which everyone knew was a wave, also behaved as a particle. The photoelectric effect, the Compton effect, the precise exchanges of energy between photons and electrons that could only be explained by treating light as discrete packets. All of this demonstrated that something universally agreed to be a wave had particle properties. De Broglie asked the obvious inverse question: if waves can be particles, can particles be waves? The question was not obviously meaningful. An electron was a particle in every experimental context where it had been studied. It had a mass. It had a charge. It could be deflected by electric and magnetic fields in ways that made perfect sense if it was a small, discrete object moving through space. Nothing about the electron suggested wave behavior. Waves spread out. Waves interfere with each other, producing the characteristic alternating pattern of reinforcement and cancellation that is the definitive signature of wave phenomena. Electrons, in every experiment conducted to that point, did none of these things. And yet de Broglie followed the logic of the symmetry between light and matter, and the mathematics led him to a specific prediction. If a particle has a momentum, mass, multiplied by velocity, then it has an associated wavelength. The wavelength is given by Planck's constant divided by the momentum. For a massive particle moving at ordinary speeds, this wavelength is extraordinarily small, far smaller than any existing instrument could detect. For an electron, moving at speeds accessible in laboratory experiments, the wavelength was small, but not impossibly so. De Broglie wrote this up as his doctoral thesis and submitted it in 1924. His thesis committee was uncertain. The idea was either brilliant or nonsensical, and they were not sure which. They were serious physicists, and they understood that the idea, if correct, would be significant. But it was also entirely without experimental support, a theoretical proposal based on symmetry and analogy rather than evidence. They sent the thesis to Einstein for evaluation. Einstein replied that de Broglie had lifted a corner of the great veil. De Broglie received his doctorate. The experimental confirmation came 3 years later, independently and almost simultaneously, from 2 different laboratories, Clinton Davison and Lester Germer, working at Bell Labs in New York, were studying how electrons scattered from a nickel crystal surface. Through a series of events that began with an accidental heating of their nickel sample, they found that electrons reflected from the crystal surface produced a pattern of intensity peaks and troughs that matched precisely the interference pattern that would be produced by waves of exactly the wavelength de Broglie's formula predicted for electrons moving at that speed. Electrons were diffracting. Diffracting is what waves do. Simultaneously, George Paget Thomson in Aberdeen, the son of J.J. Thomson, who had discovered the electron as a particle, passed electrons through thin metal films and observed the same diffraction rings. He was demonstrating that his father's particle was also a wave. Davison and Thomson shared the Nobel Prize in Physics in 1937 for demonstrating that electrons were waves. J.J. Thomson had received the Nobel Prize in 1906 for demonstrating that electrons were particles. Both prizes were correct. The mathematical framework for describing these matter waves was provided not by de Broglie, but by Erwin Schrödinger, an Austrian physicist working in Zurich. Schrödinger was 36 years old in late 1925 when he encountered de Broglie's thesis and recognized immediately that it required a wave equation, a mathematical description of how matter waves evolved over time, analogous to the wave equations that described light and sound. He spent the Christmas holiday of 1925 in the Swiss Alps in Arosa, working on the equation. He had brought his notes and his physics books. He had also, by his own account, brought a former girlfriend whose identity he declined to record in his notebooks for reasons that can be inferred. He returned from Arosa in January 1926 with the Schrödinger equation. The equation described how the wave function of a quantum system, a mathematical object that encoded the state of the system, evolved over time. The wave function was not directly observable. It was a complex valued function of position and time, and its physical interpretation was not immediately clear, not even to Schrödinger, who had written it. What Schrödinger proposed was that the wave function represented the matter directly, that the electron was, in some physical sense, spread out through the region of space where the wave function was non-zero, the way a water wave is spread out across the surface of the water. He applied the equation to the hydrogen atom and found that it reproduced Bohr's energy levels, not by assuming them, as Bohr had done Gannon, but by deriving them as the natural consequence of the wave equation applied to an electron confined near a proton. The allowed energy levels emerged from the mathematics the way harmonics emerge from a vibrating string. They were the frequencies at which the matter wave could exist stably in the confined geometry of the atom. The agreement with the observed hydrogen spectrum was exact. Schrödinger published the equation and its application to hydrogen in a series of papers in 1926 that were immediately recognized as a major advance. But the physical interpretation of the wave function remained unsettled. Schrödinger believed the wave function was a real physical wave, that the electron was literally spread out through space in the way the wave function suggested. This interpretation was attractive because it was classical in spirit. It replaced the mysterious quantum jumps of Bohr's model with the smooth, continuous evolution of a wave equation. Max Born, a German physicist working in Göttingen, proposed a different interpretation in 1926. The wave function, Born suggested, was not a physical wave. It was a probability amplitude, the square of the wave function's magnitude at any given point in space gave the probability of finding the electron at that point if a measurement were made. The electron was not spread out through space. The electron was in one place, but which place was not determined until the measurement was made. Before measurement, only the probabilities were real. This was a deeply different claim from Schrödinger's interpretation. It meant that quantum mechanics was, at its foundation, irreducibly probabilistic, not just uncertain in practice, but uncertain in principle, with no deeper level of description at which the uncertainty dissolved into determinism. Schrödinger found Born's interpretation deeply unsatisfying. He had written an equation that he intended to restore continuity and physical clarity to quantum mechanics, and Born had interpreted it in a way that made the physical world fundamentally probabilistic. The disagreement between them was never resolved. Born's interpretation became the standard one, the one taught in physics courses, used in calculations, applied in every laboratory that uses quantum mechanics. Schrödinger's dissatisfaction with his own equation's standard interpretation led him, years later, to construct a thought experiment designed to expose what he considered its absurdity: a cat, a box, a radioactive atom, a vial of poison. That thought experiment is the next chapter. Outside the window of Schrödinger's office in Zurich, the city moved through its ordinary days. The trams running along the lake, the university buildings rising above the old town, the Alps visible on clear days above the southern horizon. The wave equation sat on the page, exact and productive and deeply puzzling. An electron had a wave function. The wave function evolved smoothly and continuously according to the equation. And when a measurement was made, the wave function, spread out, extended, wave-like, somehow produced a single, definite, localized result. How this happened, what occurred during the measurement, what the wave function actually was before the measurement. These questions had no agreed answer in 1926. They have no agreed answer now. The equation works. Its predictions are confirmed to extraordinary precision, and the question of what it is describing remains, in the most fundamental sense, open. Werner Heisenberg was 23 years old when he arrived in Copenhagen in 1924 to work with Niels Bohr. He was slight, energetic, and possessed of a mathematical ability that Bohr recognized immediately as exceptional. Where Bohr thought slowly and carefully, working through ideas in long conversations that sometimes lasted entire days, Heisenberg thought quickly and abstractly, moving through mathematical structures with a speed that occasionally outpaced his physical intuition. This would turn out to be an advantage. The problem that occupied both of them through 1924 and 1925 was the same problem that had occupied everyone working on quantum theory since Bohr's atomic model. The theory worked in the sense that it produced correct predictions, but it worked by importing classical concepts like orbit and position and velocity into a domain where those concepts had no clear justification. An electron in an atom was said to be in an orbit, but the concept of an orbit implies a continuous trajectory, a path through space traced over time. And the quantum jumps between orbits, the instantaneous transitions, with nothing in between, were explicitly not trajectories. The electron did not travel from one orbit to another. It disappeared from one and appeared in the other. If the electron had no trajectory during a jump, why should it have a trajectory at any other time? Heisenberg decided to build a theory that did not use trajectories at all. In the spring of 1925, Heisenberg was suffering severely from hay fever. His face was swollen. He could barely see. He asked Bohr for 2 weeks' leave and traveled to the island of Helgoland in the North Sea, a small, rocky island with almost no vegetation and therefore almost no pollen, the air clean and cold and free of the allergens that had made his life in Copenhagen miserable. He brought his physics notes. The island was quiet in the way that small islands are quiet. The sound of the water, the wind, the absence of the urban background noise that becomes invisible until it is gone. His room in the boarding house where he stayed looked out toward the sea. He worked through the days and into the nights, following a mathematical approach he had been developing for weeks. His approach was to describe only what could be observed. Classical mechanics described the position and velocity of a particle as functions of time. X of t, v of t, continuous quantities that could in principle be measured at any moment. But in quantum mechanics, these continuous trajectories were not observable. What was observable were the frequencies and intensities of the spectral lines emitted by atoms, the light produced when electrons jumped between energy levels. Heisenberg built his theory around these observable quantities, using mathematical objects called matrices, arrays of numbers arranged in rows and columns to represent physical quantities. The mathematics was unfamiliar and technically demanding, but it produced, when applied to the hydrogen atom, exactly the same energy levels that Bohr's model produced. It also contained something unexpected. When Heisenberg examined the mathematical structure of his theory carefully, he found that position and momentum, the two quantities that classical mechanics treated as independent, simultaneously definable properties of a particle, behaved differently in his framework. In classical mechanics, if you know the position of a particle and its momentum, you know everything about its current state. The two quantities commute. It does not matter whether you measure position first and then momentum, or momentum first and then position. You get the same result either way. In Heisenberg's matrix mechanics, position and momentum did not commute. The mathematical objects representing them, when multiplied together, gave different results depending on the order of multiplication. This was not a computational inconvenience. It had a physical meaning. Heisenberg worked out what that meaning was and published it in 1927 in a paper that introduced what became known as the uncertainty principle. The uncertainty principle states that the position and momentum of a particle cannot both be precisely defined at the same time. The more precisely the position is defined, the less precisely the momentum can be defined, and vice versa. The product of the uncertainties in the two quantities must always be greater than or equal to Planck's constant divided by 4 pi. This is not a statement about measurement technology. It is not saying that our instruments are too crude to measure both quantities simultaneously, and that better instruments would allow us to do so. It is saying that both quantities do not simultaneously have precise values. There is the preciders, that the precision of position and the precision of momentum are not independent properties of the particle that we fail to measure simultaneously, but genuinely complementary aspects of the particle's state that cannot coexist. A particle with a precisely defined position has no precisely defined momentum. A particle with a precisely defined momentum is spread out through space. It has no precisely defined position. This was a direct contradiction of the classical picture of a particle as a small object located at a specific point, moving at a specific speed in a specific direction. The physical reason for the uncertainty was, at one level, clear from de Broglie's matter waves. A wave with a single, precise wavelength extends infinitely through space. It has no location. To confine a wave to a small region of space, you must combine many different wavelengths, a process called superposition, which produces a localized pulse called a wave packet. But momentum in de Broglie's framework is determined by wavelength. A wave with a single wavelength has a precise momentum. A wave packet, composed of many wavelengths, has a spread of momenta. Confining the wave in space, giving it a definite position, requires spreading it across momenta. Giving it a definite momentum, a single wavelength, spreads it across space. The uncertainty is not a failure of measurement. It is a feature of what waves are. The response from physicists was divided along lines that would persist for decades. Bohr found the uncertainty principle deeply illuminating. He had been developing a philosophical framework he called complementarity. The idea that quantum systems had complementary aspects, like wave and particle, that could not be simultaneously manifest, that the experimental arrangement chosen to reveal one aspect necessarily excluded the other. Sandberg's principle fit this framework precisely and gave it mathematical content. Einstein found it deeply troubling. He and Bohr argued about the uncertainty principle at the Solvay conference in Brussels in October 1927, in a series of exchanges that became legendary in the history of physics. Einstein would arrive each morning with a new thought experiment designed to show that the uncertainty principle could be circumvented, that a clever enough experimental arrangement could, in principle, measure both position and momentum. Simultaneously, Bohr would spend the day working through the thought experiment and return the following morning with a demonstration that the uncertainty principle survived. The exchanges were conducted with complete mutual respect and complete mutual disagreement. Einstein never accepted the uncertainty principle as a fundamental feature of reality. He believed it reflected the incompleteness of quantum mechanics, that there was a deeper level of description, not yet found, at which the uncertainty dissolved into determinism. Bohr believed the uncertainty was fundamental, not a symptom of incompleteness, but a feature of what quantum mechanics was actually saying about the nature of reality. This disagreement was never resolved between them. Heisenberg returned from Helgoland with clearer eyes and a new mechanics. The hay fever had retreated. The island had been quiet and cold and empty of everything except the physics he had carried with him. He had built a theory from observable quantities alone, excluded the unobservable. Trajectories that classical mechanics assumed, and found that the mathematics produced not only the correct spectral lines, but a fundamental relationship between position and momentum that nobody had anticipated. The uncertainty was not in his instruments. It was not in his calculation. It was in the particle itself, in what the particle was at the most fundamental level of its description. A particle was not a small object at a specific location moving at a specific speed. It was something for which position and momentum were complementary rather than independent. Something that, when pressed for a precise position, refused to have a precise momentum, and when pressed for a precise momentum, refused to have a precise position. What it was, exactly, between measurements, whether it had any properties at all when not being observed, was a question that Heisenberg's paper did not answer. That question would be asked most sharply and most uncomfortably by Schrödinger himself, with a cat and a box and a radioactive atom. That is the next chapter. The island was behind him now. The North Sea was cold and gray in the late afternoon, and in the mathematics he carried back to Copenhagen, the uncertainty sat quietly, patient and absolute, refusing to be argued away. The city of Oxford was quiet in the early autumn of 1935. The stone buildings of the university had stood for centuries, their walls weathered by English rain and softened by ivy that climbed slowly upward year after year. The mornings arrived cool, with thin mist lingering over the college gardens before the sun burned it away. Students crossed the courtyards carrying books beneath their arms, while inside the physics departments, conversations continued about a subject that had become impossible to ignore. Quantum mechanics worked. Its equations predicted experiments with astonishing precision. Spectral lines, chemical bonds, atomic behavior, the properties of matter itself, all could now be calculated with remarkable success. And yet no one could agree on what the equations actually meant. The mathematics was clear. Reality was not. Among those most troubled by this situation was Erwin Schrödinger. Only 9 years earlier, he had written the wave equation that had transformed quantum theory. He had hoped his equation would replace the mysterious jumps of Bohr's atom with something continuous and understandable. Instead, Max Born's interpretation had become dominant. According to Born, the wave function did not describe a physical wave spread through space. It described probabilities. B. For a measurement. An electron was not simply hidden somewhere waiting to be discovered. Instead, every possible outcome existed only as different probability encoded within the wave function. When a measurement occurred, one outcome appeared. The others disappeared. Physicists called this process the collapse of the wave function. The mathematics required it. But nowhere in Schrödinger's equation did such a collapse actually exist. The equation described only smooth, continuous evolution. There was no line that said, "Now reality chooses." There was no mathematical instruction explaining why one possibility became real, while all the others vanished. Something essential seemed to be missing. Schrödinger believed that if this interpretation were taken seriously, it led to conclusions so strange that everyone would recognize its absurdity. He decided not to argue with equations. Instead, he invented a story. It was not an experiment anyone intended to perform. It was a thought experiment, a carefully imagined situation designed to reveal the consequences of an idea. Imagine, Schrödinger said, a sealed steel box. Inside the box sits a cat. Next to the cat is a tiny amount of radioactive material. Radioactive atoms behave unpredictably. No one can say exactly when a particular atom will decay. It might decay within the next hour. It might not. Connected to the radioactive atom is a detector. If the detector registers a decay, it activates a small hammer. The hammer breaks a glass vial. Inside the vial is poison. If the vial breaks, the poison fills the box. The cat dies. If the atom does not decay, nothing happens. The cat remains alive. The box is then closed. No one can see inside. Quantum mechanics describes the radioactive atom using a wave function. Before observation, the atom exists in a superposition, a mathematical combination of both possibilities. Decayed, not decayed. If the detector is connected to the atom and the hammer is connected to the detector and the poison is connected to the hammer, then the mathematics extends through the entire chain. Detector triggered, detector not triggered, poison released, poison contained, cat dead, cat alive. According to the standard interpretation, until someone opens the box and performs a measurement, the entire system remains in superposition. The cat is not simply unknown. The cat is mathematically described as both alive and dead. Schrödinger never intended people to believe this literally. The example was meant as a criticism. He wanted to demonstrate that applying quantum rules directly to everyday objects produced conclusions that seemed impossible to accept. A single electron existing in multiple possibilities was already difficult. A living animal existing in multiple contradictory states seemed completely unreasonable. Surely, Schrödinger argued, something had gone wrong before reaching that conclusion. Yet, the more physicists examined the thought experiment, the more uncomfortable they became. The mathematics itself contained no obvious mistake. The equations treated atoms, detectors, poison, and cats according to the same principles. Where, exactly, should quantum behavior stop? At the atom? At the detector? At the glass vial? At the cat? At the human observer? No equation answered the question. The boundary between the quantum world and the everyday world had never been defined. Niels Bohr believed the problem arose from asking the wrong question. To Bohr, quantum mechanics was not attempting to describe reality. Independent of observation, it described what could be said about experiments. The measuring apparatus belonged to the classical world. The quantum system belonged to the microscopic world. Trying to separate them completely was impossible because every observation required an interaction between the two. Albert Einstein found this deeply unsatisfying. He had accepted quantum mechanics as an extraordinarily successful computational tool. He had helped create it. His own work on light quanta had opened the door decades earlier. But he could not accept that physical reality depended on observation. The moon, he once asked rhetorically, does not cease to exist when no one is looking at it. Reality, Einstein believed, should exist independently of measurements. Objects should possess definite properties, whether anyone observes them or not. Quantum mechanics seemed to deny this. His concern became even sharper in 1935, the same year Schrödinger introduced his famous cat. Together with Boris Podolsky and Nathan Rosen, Einstein published another thought experiment. It would later become known simply as the EPR paradox. Imagine two particles interacting briefly before flying apart in opposite directions. Quantum mechanics allows these particles to become entangled. Their properties become linked in such a way that describing one independently of the other is no longer possible, even after traveling enormous distances apart. They remain connected mathematically. Mafurage, one particle. The description of the other changes instantly. Suppose the particles travel to opposite sides of the galaxy. One remains on Earth. The other reaches a distant star. If measuring the first immediately determines the state of the second, something remarkable appears to happen. Information seems to travel faster than light, but Einstein's theory of relativity had established 30 years earlier that nothing could travel faster than light. The two ideas appeared incompatible. Einstein called this spooky action at a distance. He disliked the phrase. He disliked the idea even more. His conclusion was straightforward. Quantum mechanics must be incomplete. Some hidden information, variables not included in the theory, must already determine the outcomes before measurements occur. If those hidden variables were discovered, certainty would return, probability would disappear. Bohr responded almost immediately. His reply was respectful, careful, and famously difficult to read. He argued that Einstein's assumptions about measurement and physical reality were rooted in classical thinking that quantum mechanics had already surpassed. The properties of quantum systems, Bohr insisted, could not be discussed independently of the experiments used to measure them. The debate solved nothing. Each man remained convinced. Einstein believed reality existed independently of observation. Bohr believed observation was inseparable from physical description. Neither persuaded the other. The discussions continued through conferences, letters, and private conversations over the following decades. Students watched these exchanges with fascination. The greatest physicists in the world agreed completely on the equations. They disagreed profoundly on their meaning. Meanwhile, laboratories continued producing experiments that matched quantum predictions with extraordinary accuracy. Atoms behaved exactly as the mathematics expected. Electrons interfered like waves. Photons arrived like particles. Probabilities predicted measurements perfectly. Technology advanced. Understanding did not. The cat remained inside its imaginary box. It never existed as a real laboratory animal. Yet, it became one of the most famous cats in history because it represented a question rather than an answer. What is reality before observation? Does nature choose an outcome only when measured, or does every possibility exist simultaneously until experience reveals one of them? No consensus emerged. Even today, physicists teach Schrödinger's equation, calculate quantum systems with astonishing precision, and build technologies that rely upon those calculations. Quantum computers, lasers, semiconductors, magnetic resonance imaging, all depend on quantum mechanics. Yet ask what the wave function truly represents. And different physicists may still offer different answers. Outside Oxford, evening settled gently across the old colleges. The bells rang the hour above narrow streets, worn smooth by centuries of footsteps, feet. In countless laboratories around the world, atoms quietly followed equations that nobody doubted. Only their meaning remained uncertain. Inside an imaginary steel box that never truly existed, a cat waited patiently, not to teach biology, but to remind every generation of physicists that predicting reality and understanding reality are not always the same thing. The city of Geneva was quiet in the summer of 1964. The Alps stood motionless beyond the horizon, their snow-covered peaks catching the morning light, while physicists gathered inside lecture halls and research institutes across Europe. The Second World War had ended nearly 2 decades earlier. Nuclear physics had transformed the world. Quantum mechanics had become the foundation of chemistry, electronics, and solid-state physics. Few scientists doubted that the equations worked. Many still wondered whether they were complete. Albert Einstein had died 9 years earlier, in April of 1955. He never accepted the standard interpretation of quantum mechanics. To the end of his life, he believed that nature possessed a deeper level of reality, hidden beneath the probability described by the wave function. Somewhere, He thought there had to be variables that quantum mechanics failed to describe. If those hidden variables were discovered, certainty would return. The universe would once again become deterministic. For years, this disagreement remained largely philosophical. Bohr believed one thing. Einstein believed another. Neither side could design an experiment capable of deciding who was right. Then, a quiet Irish physicist changed that. John Stuart Bell was working at CERN near Geneva. Unlike many theoretical physicists, Bell was deeply uncomfortable with debates that could never be tested. Arguments about philosophy interested him only if they eventually produced measurable consequences. Einstein's objections fascinated him, not because Bell necessarily agreed with Einstein, because Einstein's questions deserved an answer. Bell began studying the EPR paradox carefully. The paradox involved two particles that had interacted before separating. Quantum mechanics described them with a single shared wave function. Even when the particles traveled far apart, their properties remained mathematically connected. Mevorch one particle. The state of the other became immediately determined. Einstein considered this impossible. If the particles were separated by enormous distances, no physical influence could travel between them faster than light. Therefore, he argued, the particles must already possess definite properties before measurement. Quantum mechanics simply failed to describe those hidden properties. Bell asked a simple question. Suppose Einstein was correct. Suppose hidden variables really existed. Would such a universe produce exactly the same experimental results as quantum mechanics? The answer surprised everyone. No, in 1964, Bell derived a mathematical relationship that became known as Bell's inequality. The equation itself was elegant. Its meaning was profound. Any theory based on local hidden variables, that is, a theory in which physical properties already exist before measurement and no influence travels faster than light, must satisfy Bell's inequality. Quantum mechanics predicted that, under certain conditions, the inequality would be violated. For the first time, philosophy had become physics. This was no longer a matter of interpretation. It was an experimental question. Nature herself could decide. If experiments obeyed Bell's inequality, Einstein would be right. If they violated it, then no local hidden variable theory could explain reality. The challenge was extraordinary. Testing Bell's theorem required creating pairs of entangled particles and measuring their properties with enormous precision. In the 1960s, the technology barely existed. Early experiments were performed by physicists, including John Clauser in the United States. Their results already leaned toward quantum mechanics. Bell's inequality appeared to be violated, but the experiments still contained possible loopholes. Some physicists argued that subtle flaws in the equipment could explain the results. More precise tests were needed. Those tests arrived in France. A law Aspect was a young physicist working at the Institut d'Optique near Paris during the late 1970s. He believed Bell's theorem deserved the most careful experimental examination possible. His team designed an experiment using pairs of entangled photons. The photons were emitted together from excited calcium atoms. Once created, they traveled in opposite directions towards separate detectors. Each detector measured the photon's polarization. Polarization describes the orientation of a light wave. A photon may pass through a polarizing filter aligned in one direction but not another. Quantum mechanics predicted that measurements performed on one photon would remain correlated with measurements performed on its distant partner in a way impossible under local hidden variable theories. The detectors themselves became a crucial part of the experiment. If they remained fixed throughout the measurement, critics could argue that hidden variables somehow anticipated the detector settings before the photons left their source. Aspect solved this problem elegantly. During the photon's flight, the orientation of the detectors changed rapidly. Settings were switched while the photons were already traveling. There was no time for any signal moving at the speed of light to inform one photon about the detector chosen for the other. If the correlations still appeared, local hidden variables would be extraordinarily difficult to defend. In 1982, the experiments were completed. The results matched quantum mechanics. Bell's inequality was violated again and again. Within experimental uncertainty, every prediction of quantum mechanics proved correct. Einstein's local hidden variables could not explain the observations. The scientific community paid close attention. Bell himself had not claimed that quantum mechanics was complete. His theorem established something more specific. Any theory attempting to restore classical certainty had to abandon at least one deeply held assumption. Either physical properties were not predetermined before measurement, or influences in nature were not entirely local. Reality could no longer resemble the comfortable picture inherited from classical physics. Entanglement was not simply a mathematical convenience. It appeared to be a genuine feature of nature. Two particles could behave as parts of a single quantum system, even after traveling vast distances apart. This did not allow messages to travel faster than light. No usable information could be transmitted instantaneously. Einstein's theory of relativity remained intact, but the correlations themselves were unlike anything classical physics had imagined. Later, generations of physicists refined the experiments further. Detector efficiencies improved. Distances increased. Loopholes were closed one after another. Pairs of entangled photons were separated by kilometers. Eventually, experiments stretched across cities, then between islands, then between Earth and satellites, orbiting hundreds of kilometers above the planet. Each new test reached the same conclusion. Quantum mechanics continued to win. In 2022, nearly 60 years after Bell published his theorem, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger. Their experiments had transformed entanglement from a philosophical curiosity into an experimentally established property of the universe. By then, entanglement was no longer merely an intellectual puzzle. It had become a practical resource. Quantum cryptography relied upon it to detect eavesdropping. Quantum teleportation used entanglement to transfer quantum states between distant systems. Quantum computers were being designed around entangled qubits whose collective behavior could solve problems beyond the reach of ordinary machines. The strange phenomenon that Einstein had called spooky action at a distance had become one of the most valuable tools in modern science. Yet its deeper meaning remained uncertain. Did entangled particles somehow remain connected across space? Did measurement reveal reality or help create it? Different interpretation continued to offer different answers. The experiments settled only one question. Nature did not behave according to Einstein's local, hidden variable picture. Outside the laboratory near Paris, evening descended over quiet streets lined with trees. The detectors cooled. The electronics fell silent. Inside stacks of printed data, tiny flashes of light had answered a question that had challenged physicists for nearly half a century. The universe was more deeply connected than classical intuition allowed. Not because anyone wished it to be, because every careful experiment kept saying the same thing. The mathematics that had once seemed impossible continued to describe reality with extraordinary precision, and beyond those invisible connections lay an even stranger possibility. If information could exist not merely as zeros and ones, but as quantum superpositions and entangled states, then entirely new kinds of machines might become possible. Machines that did not simply calculate faster, but calculated according to the rules of quantum reality itself. The control room was almost silent. Rows of computer screens glowed softly in the dim light. Thick bundles of cables disappeared beneath raised floors. Refrigeration systems hummed steadily in the background, keeping delicate equipment colder than the emptiness between the stars. Behind layers of shielding and vacuum chambers sat one of humanity's newest kinds of machines, not powered by steam, not powered by electricity alone, but by the same strange quantum rules that had confused physicists for more than a century. By the beginning of the 21st century, quantum mechanics had become one of the most successful scientific theories ever created. Every experiment performed over the previous 100 years had confirmed its predictions with astonishing accuracy. Fenforamin, the laser, the transistor, the computer chip, magnetic resonance imaging, Otnock clocks, solar panels, modern chemistry. Even the GPS receiver inside an ordinary smartphone depended on corrections derived from Einstein's relativity and quantum physics, working together. Most people used quantum technology every day without ever realizing it. The theory that once seemed like an impossible mathematical curiosity had quietly become part of everyday life. Yet physicists were no longer satisfied with simply using quantum mechanics. They wanted to build machines that thought according to its rules. A classical computer stores information using bits. Each bit exists in one of two states, del or 1. Every photograph, every movie, every piece of music, every website, every scientific simulation is ultimately reduced to unimaginably long strings of zeros and ones. Quantum computers replace bits with quantum bits, or qubits. A qubit can exist as 0, it can exist as 1, or, through superposition, it can exist as a combination of both until measurement. 1 qubit is interesting. 2 qubits become far more powerful because they can also become entangled. As more qubits are added, the number of possible quantum states grows extraordinarily quickly. Instead of examining one possibility after another, certain calculations can explore many possibilities simultaneously through carefully controlled quantum interference. This does not mean a quantum computer instantly solves every problem. Many tasks remain faster on ordinary computers. But for certain kinds of calculations, simulating molecules, optimizing complex systems, searching enormous mathematical spaces, and factoring extremely large numbers, quantum algorithms promise capabilities that classical machines may never achieve efficiently. Building such computers, however, has proven remarkably difficult. Quantum states are fragile, a tiny vibration, a stray magnetic field. A small increase in temperature, even a single interaction with the surrounding environment, can destroy a delicate superposition. This process is called decoherence. Instead of behaving according to quantum rules, the system begins behaving classically. The information is lost. For decades, scientists believed practical quantum computers might remain impossible. Yet, year after year, engineering improved. Researchers learned how to isolate qubits more carefully. They developed methods for correcting quantum errors before they accumulated. Companies and laboratories around the world constructed increasingly sophisticated quantum processors. The machines remained imperfect, but they continued improving. Another unexpected application emerged from Einstein's greatest objection: entanglement. The strange connection he once dismissed as spooky action at a distance became the foundation of quantum cryptography. Imagine two people wishing to exchange a secret message. In ordinary communication, an eavesdropper might secretly copy the information without leaving any trace. Quantum mechanics changes that possibility. Measuring a quantum state inevitably disturbs it. Any attempt to intercept the communication changes the particles themselves. The intrusion cannot remain perfectly hidden. Nature, in effect, announces that someone has been listening. Instead of relying only on mathematical difficulty for security, Quantum cryptography relies on the laws of physics themselves. Then came another idea, whose name sounded almost like science fiction: quantum teleportation. The word immediately suggests people disappearing in one place and appearing in another. That is not what physicists mean. Quantum teleportation does not transport matter. It transports information. Specifically, it transfers the quantum state of one particle onto another distant particle using entanglement combined with ordinary communication. The original state disappears. The distant particle acquires it. Nothing travels faster than light. No object vanishes into thin air. Yet, the transfer of quantum information has now been demonstrated repeatedly across laboratories, optical fibers, and even between satellites orbiting Earth. The ideas that once seemed impossible had quietly become routine experiments. Still, for all these remarkable achievements, one question remained untouched. What is quantum mechanics actually telling us about reality? More than a dozen serious interpretations now compete to answer that question. The Copenhagen interpretation, associated with Bohr, treats the wave function primarily as a tool for predicting observations. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every possible quantum outcome actually occurs. Instead of one reality choosing a single result, the universe continually branches into countless histories. In one branch, an electron moves left. In another, it moves right. Every possibility exists somewhere. Other physicists favor pilot wave theory, originally suggested by Louis de Broglie and later developed by David Bohm. In this view, particles always possess definite positions. An invisible quantum wave guides their motion. The randomness of quantum mechanics is only apparent. Beneath it lies a hidden order. Still, others explore entirely different interpretations. Objective collapse theories, relational quantum mechanics, cubism, each preserves the mathematics. Each tells a different story about what the mathematics means. And despite decades of debate, no experiment has yet definitively selected one interpretation over the others. It is one of the rare situations in science where multiple explanations produce exactly the same measurable predictions. The equations remain silent. Reality keeps its secret. Perhaps this is the most remarkable feature of quantum mechanics. Never before had humanity possessed a scientific theory that could predict nature with such extraordinary precision while leaving the nature of reality itself so deeply mysterious. Newton explained falling apples and planetary motion. Maxwell united electricity, magnetism, and light. Einstein reshaped space and time. Quantum mechanics did something different. It revealed limits, not merely in technology, but in intuition itself. The universe is not obligated to resemble everyday experience. It is not required to satisfy common sense. Nature existed for billions of years before human beings evolved. Our brains developed to understand forests, rivers, stones, and sunlight. Not atoms, not probability, amplitudes, not wave functions spread across invisible mathematical spaces. Perhaps it should not surprise us that reality, at its deepest level, refuses to fit comfortably inside instincts shaped on the African savanna. Richard Feynman, one of the greatest physicists of the 20th century, once offered an observation that remains as honest today as when he first said it. I think I can safely say that nobody understands quantum mechanics. He did not mean the mathematics. Physicists understand the calculations extremely well. They build technologies from them. They predict experiments with extraordinary precision. What remains elusive is something older than mathematics, meaning. Outside the laboratory, the night sky looks exactly as it always has. The stars shine quietly across distances so immense that many of the photons reaching Earth tonight began their journeys before human civilization existed. Each photon travels according to quantum mechanics. Each atom in your body obeys the same equations discovered by Planck, Einstein, Bohr, Schrödinger, Heisenberg, Bell, and countless others. Without quantum mechanics, the sun would not shine. Chemistry would not exist. Life itself could never have emerged. The strange world hidden beneath ordinary experience is not separate from us. It is us. Every heartbeat, every breath, every memory, every thought depends upon countless quantum events unfolding silently beneath awareness. More than a century has passed since Max Planck reluctantly introduced a tiny constant into an equation he believed was only a mathematical trick. He could not have known that this single idea would overturn classical physics, reshape modern technology, challenge philosophy, and reveal that reality is stranger than anyone had imagined. The journey began with a problem no one expected, a warm piece of glowing metal. It ended by transforming our understanding of existence itself. And perhaps the most comforting thought is this: after more than 100 years of discovery, after Nobel Prizes, satellites, particle accelerators, quantum computers, and experiments of astonishing precision, the universe still holds mysteries. There are still questions worth asking, still ideas waiting to be discovered, still quiet moments when someone looks at nature and notices something everyone else has overlooked. The story of quantum mechanics is not finished. It is simply the chapter we have reached so far. So as the night grows quieter and the stars continue their patient journey across the sky, the atoms around you remain busy, following rules written into the fabric of the universe long before anyone gave them names. They ask for nothing. They simply exist. And perhaps, somewhere beyond the limits of today's understanding, another curious mind is already preparing to write the next chapter.